What's the deal with the heat index and the dew point? Can it really be 100 degrees and 100% humidity? And can Antarctica really be a desert? And why and where do clouds form, and is that different than fog? Well, in today's video we answer these questions and more, calculate how much moisture is in the air, and then I'll show you how to make clouds in a bottle and see how it's all related to one commonly misunderstood thing: relative humidity. If we could find the mass of the air inside this cube, it would be about 1 kilogram or 2.2 pounds. And do you know how much water I could evaporate into this cube of air before the air was totally saturated and could hold no more water vapor? Is it 14 grams, a half a gram, or is it closer to 50 grams? The answer, well, that's where humidity gets interesting, because it's all relative. At 70 degrees Fahrenheit, a kilogram of air can hold 14 grams of water vapor. So when I have 14 grams in it, that is 100% relative humidity. And if the air can hold 14 grams of water vapor, but I only evaporated 7 grams into it, that's only holding half of what it could. That's 50% humidity. The air's just not living up to its full potential. But what if it's like negative 10 degrees? You know, Antarctic cold. Well, that kilogram of air could only hold about a half a gram of water vapor before it was saturated in 100% humidity. So 100% humidity in Antarctica is far drier than 100% humidity somewhere with 70-degree air. And that also explains why Antarctica is technically a desert. It's just too cold to even hold moisture in the air to precipitate. But what about summertime in Florida, which I'm not gonna lie, sounds kind of nice right now. If it were 100 degrees there, could the humidity be 100%? Well, 100-degree air can theoretically hold close to 50 grams of evaporated water, but that almost never happens. Even being just 70% humidity at 100 degrees is really, really humid. It would have 35 grams of water vapor in a cube of air. That's over 2 times as much as 100% humidity at 70 degrees. Enough to get people telling stories when they come home from vacation. I'm sure it felt like it must be 100% humidity, but it was probably just hyperbole. And this brings me to the heat index, another common addition to weather forecasts and directly related to relative humidity. You see, humans cool down by sweating, where our body heat leaves with the evaporating sweat. And in really humid air, less evaporation happens. In fact, if the humidity is 100%, evaporation pretty much stops and things just don't dry. Because at this point the air is like a sponge full of water that can't hold any more. And if there's no evaporation, then you can't cool down. And the same goes for your dog, who cools down with evaporating saliva while it pants. And because of this, we have the heat index, which is what the weather feels like instead of what it actually is. Here's the heat index chart. At 100 degrees, even 65% humidity feels like 136 degrees. It's miserable. The chart doesn't even go to 100% humidity at this temperature because it doesn't happen. It would feel like you were on Venus. Now, before I move on to all the other fascinating stuff that has to do with relative humidity, if you ever want to calculate your own relative humidity, whether out of curiosity or a severe distrust in the weather establishment, all you need are 2 analog thermometers, room temperature water, a small piece of paper towel, some mildly strong shoulder muscles, and something to fan with. Start by dipping a piece of paper towel in the water. Now wrap that piece of paper towel all the way around one of the bulbs of the thermometers. Keep the other thermometer dry. Then you can start fanning until the temperature of the thermometers stop changing, and record the temperature change of both. Then use this chart. When my kids did this, my dry thermometer was 70 degrees, the wet one dropped about 15 degrees, and on the chart that falls right at 36% humidity. Nice job! And remember, if the humidity were 100%, there'd be no evaporation and no drop in temperature. So the more that temperature drops, the less humid it is. Thanks guys, now go get the neighbor's humidity. Now, I'm excited about the next part of this video because this is something that not everybody knows about, but they probably should. It's the dew point. And the dew point is the gateway to understanding humidity, clouds, precipitation, fog, dew. Let's say it's 50% humidity right now, and the temperature of the air is 70 degrees. A kilogram of air would have 7 grams of water vapor in it, but it can still hold 7 grams more. But what happens if the temperature begins to drop? So does the maximum amount of the water vapor that the air can hold. And here, something happens, because at 50 degrees, the air can only hold 7 grams of water vapor, and that's what's in it. You have reached the dew point, the temperature that the air can no longer hold all of the water vapor in it, and the relative humidity is 100%. So what becomes of this water vapor? Well, it begins to condense and turn back into a liquid. If the air reaches the dew point in the sky, that's where clouds begin to form. If this happens on the ground, we get fog. Or if the air is touching something colder than the dew point, water vapor condenses onto that thing, like a glass of cold water or grass. And if the dew point is below freezing, it condenses straight into frost. Understanding relative humidity and its sibling dew point explains a lot of the things we see and experience. We even use it to forecast rain or snow, because guess what happens when the temperature keeps dropping past the dew point? That's right, precipitation. Now for a quick segment I like to call Nature Makes Beautiful Clouds, So Why Can't I? Well, you can. You can do it by taking a hot shower, or opening up the dishwasher mid-cycle, or breathing outside on a cold day. See the warm, moist air quickly cooling down past the dew point? Or you can make a cloud in a bottle at home by doing the following. If you've ever wanted to make a cloud, it's actually really easy. All you need is a plastic bottle, hot water, and some matches. And here's how you do it. You start by putting the hot water in the bottle, maybe about an inch or so into the bottom. Then you seal it up really fast so you don't lose that hot air full of water vapor. The next step is you get a match, light it, and then blow it out inside the bottle so that some smoke goes in there. The smoke acts as what's called a condensation nuclei. It gives something for the water vapor to condense out onto when it forms into a cloud. The final step is that you need to get the air in this bottle to go down a little bit in temperature, which might seem hard, but it's pretty easy because all you have to do is this. You squeeze to increase the pressure in the bottle and increase the temperature, and then you release to decrease the temperature and pressure inside the bottle, and there you have a cloud in the bottle. Once again, you squeeze and release, and you have your cloud in the bottle. What happens is the temperature of the air decreases below the dew point temperature. The air can no longer hold all the water vapor inside of it, so it condenses out into little tiny droplets on the smoke particles that are floating invisibly in there. There's your cloud. Bye, little cloud. I hope you enjoyed this video about relative humidity, water vapor, dew point, fog, frost, clouds, and everything else affected by water in our atmosphere. If so, please like, subscribe, and leave a comment. Stay curious.